In this video, I will teach you how to answer questions relating position, velocity, and acceleration. If you appreciate the content, please give it a like. Words like distance, location, position, and displacement describe where you are in relation to a fixed point. A position function can be represented by any variable. However, if you're talking about a particle or an object that's moving horizontally, you will often see it represented by x of t. The position of a particle or object that's moving vertically will often be represented by y of t. S of t is often used for the position of a particle or object that's moving diagonally, but again, these could be any letter. Long ago, we memorized the relationships between f, f prime, and f double prime. The same relationships exist between position, velocity, and acceleration, because velocity is the derivative of the position function, and acceleration is the derivative of the velocity function. Acceleration is the second derivative of the position function. So basically, s is like the original function f, v is like f prime, and a is like f double prime. Velocity is the rate of change of position. Note that a positive velocity means position is increasing, negative velocity means position is decreasing, and zero velocity means the graph of position has a horizontal tangent line. What comes up even more often is that the sign of velocity tells you the direction in which you are moving. Positive velocity means the particle or object is moving to the right, or up, or forward. A negative velocity means the object is moving left, or down, or backwards. Zero velocity means the particle or object is at rest. This is a key phrase. Whenever you see the words at rest, I want you to automatically think, okay, the velocity is equal to zero. Always keep in mind that the derivative of a position function gives you the velocity function. Velocity is the rate of change of position, so average velocity is the average rate of change of the position function. Hopefully, you will recognize this formula from AP Pre-Calculus for the average rate of change of s from A to B. S at B minus S at A over B minus A. This is the slope of the secant line from A to B on the position graph. When we just say velocity as opposed to average velocity, we mean the instantaneous velocity at time t, and that's equal to s prime, the derivative of the position function. In other words, the instantaneous rate of change of the position function. Back in Unit 2, we learned that the derivative is the slope of a curve at a point. So velocity, which equals s prime of t, is the slope of the tangent line on the position graph. If we take the derivative of velocity, we get acceleration. Acceleration is the rate of change of the velocity function. Positive acceleration means velocity is increasing. Negative acceleration means velocity is decreasing, and acceleration of zero means the graph of the velocity function has a horizontal tangent line. Since acceleration is the rate of change of velocity, then average acceleration will be the average rate of change of velocity. That's why the average acceleration from A to B is given by v at B minus v at A over B minus A. Again, this is just your average rate of change formula from AP Pre-Calculus. In this case, the average rate of change of velocity from A to B. Graphically, average acceleration is the slope of the secant line on a velocity graph from A to B. When we just say acceleration as opposed to average acceleration, we mean the instantaneous acceleration. That's v prime, the instantaneous rate of change of velocity. Since velocity is the derivative of the position function and acceleration is the derivative of the velocity function, that means acceleration is the second derivative of the position function, s double prime. Acceleration is the slope of the tangent line on a velocity graph. We need to talk about speed. This is a word that you use every day in common speech. However, it has a very specific meaning in calculus. In calculus, speed is the absolute value of velocity, which is given by this expression. So forget about your everyday uses of the word speed. When I say speed, I want you to think, oh, the absolute value of velocity. I want you to memorize this. This is going to come up a lot. Speed is increasing when velocity and acceleration have the same sign, like they're both positive or they're both negative. Either way, speed is increasing. Speed is decreasing when velocity and acceleration have opposite signs. If one's positive and one's negative, then the speed is decreasing. Let's go back to when speed is increasing, when velocity and acceleration have the same sign. One way for this to happen is if velocity is positive and acceleration is also positive. However, if acceleration is positive, it means velocity is increasing. So another way to say that velocity is positive and acceleration is positive is to say that velocity is both positive and increasing. Another way for velocity and acceleration to have the same sign is if they are both negative. A negative acceleration means velocity is decreasing. So instead of saying velocity is negative and acceleration is negative, we could say velocity is negative and decreasing. Putting it all together, we can say that speed is increasing when velocity and acceleration have the same sign, which is to say that velocity is positive and increasing, or velocity is negative and decreasing. I'm teaching you this second way of saying it because we have learned that our justifications must always be based on the graph that we are given. So if we are given a graph of velocity, we can't be mentioning acceleration. So the only way to say that speed is increasing would be to say that velocity is positive and increasing, or velocity is negative and decreasing. Similarly, though speed is decreasing when velocity and acceleration have opposite signs, if we are given the graph of velocity and we're not allowed to mention acceleration, we can say speed is decreasing because velocity is positive and decreasing, or speed is decreasing because velocity is negative and increasing. Make sure you have memorized this chart. You should be able to write it from memory on a piece of scratch paper or in the margin for your next test or quiz. Given each description, sketch the graphs illustrating the basic shape of the position, velocity, and acceleration graphs. Answers can vary somewhat. Number 1. Moves forward with constant velocity. Direction is given by the sign of the velocity function. So, if the particle or object is moving forward, that means a positive velocity. And if velocity is positive, we know position is increasing. If the velocity is constant, then the velocity graph should be horizontal. And if the velocity graph is horizontal, then the acceleration is 0. This makes sense because if the velocity is constant, the rate of change of velocity, the acceleration, would be 0. Also, if the velocity is constant, the position function must be linear. Remember, velocity is the derivative or the slope of the position function. The only way the velocity function will be constant is if the position function has a constant slope, thus linear. Another way to think about it is that if velocity is horizontal, that means it is neither increasing nor decreasing. So therefore, the position function is neither concave up nor concave down, thus linear. So the position function had to be increasing and linear, which is what I have drawn. The velocity function needs to be positive and horizontal, like so. The acceleration function is 0, so kabam. Number 2, moves backward with decreasing velocity. The sign of velocity indicates direction, so moves backwards means velocity is negative. If velocity is negative, we know the position function is decreasing. We are straight up told that the velocity function is decreasing, and if velocity is decreasing, the acceleration function is negative. Also, if velocity is decreasing, it means the position function is concave down. So we are ready to draw. The position function must be decreasing and concave down, like this. Velocity must be negative and decreasing, like this. I'm drawing it linear. We aren't told that it had to be linear, but I'm keeping it simple, negative and decreasing. The acceleration function is simply negative. That's all we know, so I'm just going to draw it like this. By the way, on number 2, they didn't ask us this, but would the speed be increasing or decreasing? We know that speed is increasing on number 2 because velocity and acceleration have the same sign. Number 3, moves downward with decreasing speed. The direction corresponds to the sign of velocity. So if the object is moving downward, the velocity is negative. And if the velocity is negative, that means the position is decreasing. If the speed is decreasing, we know that the velocity function and the acceleration function have opposite signs. Since we already know velocity is negative, then acceleration must be positive. And if acceleration is positive, it means velocity must be increasing. And if velocity is increasing, the position function is concave up. We must draw the position function as decreasing and concave up, so something like this would work. The velocity function must be negative and increasing, so something like this would work. And all we know about the acceleration function is that it is positive, so I'm just going to keep it simple. Number 4, moves to the right with positive acceleration. Moving to the right means the velocity must be positive. And if the velocity is positive, the position is increasing. Positive acceleration. We are straight up told that the acceleration is positive. And if acceleration is positive, it means velocity is increasing and position is concave up. That's enough to draw. We need to draw a position so that it is increasing and concave up. So something like this. The velocity must be positive and increasing. So this would work. And acceleration is positive. So I'm just going to do this. They did not ask us about speed, but on number 4, would the speed be increasing or decreasing? We know the speed is increasing because velocity and acceleration have the same sign. You can also determine whether speed is increasing or decreasing based strictly on the description of the velocity function. If these words sound similar, then the speed is increasing. If the velocity words sound opposite, then the speed is decreasing. In this case, velocity is positive and increasing. Do you hear how those sort of sound similar? So the speed is increasing. Look back on number 3. Velocity is negative and increasing. Hear how these sort of sound opposite. So the speed is decreasing. Then back to number 2. The velocity was negative and decreasing. See how these sound sort of similar? So the speed is increasing. A bug crawls along the y-axis. Its velocity at time t for t greater than or equal to 0 is given by the function v of t, which is graphed to the right. Number 5. What is the bug's average acceleration between t equals 0 and t equals 6? Show your work. Our thought process is acceleration is the rate of change of velocity, and average acceleration is the average rate of change of velocity. So we're going to set up the formula for the average rate of change of velocity. On the interval from 0 to 6, that's v at 6 minus v at 0 over 6 minus 0. Let's see, what is the velocity at 6? Well, that's 1. The velocity at 0 is 3, so that's 1 minus 3 over 6 minus 0. This is negative 2 over 6, which simplifies down to negative 1/3. When, if ever, is the bug at rest? Justify your answer. The phrase at rest means that velocity is equal to 0. This is the velocity graph, and we can see that velocity is equal to 0 here and here. We say t equals 3 and t equals 8 because velocity is equal to 0. Number 7. When, if ever, does the bug change direction? Justify your answer. Direction is indicated by the sign of velocity. So if the bug is changing direction, the velocity is changing signs. So when does the velocity change signs? The only place is at t equals 8, where the velocity goes from positive to negative. We say t equals 8 because velocity changes signs. Number 8. When, if ever, is the bug's acceleration positive? Justify your answer. Obviously, we don't have the acceleration graph, we have the velocity graph. This is where the chart sort of comes in. If we want the acceleration to be positive, the velocity must be increasing. The velocity is only increasing on this part of the graph. That's the interval from 3 to 6. We say on the interval from 3 to 6 because velocity is increasing. Remember, your justification must always be based on the graph you are given. That's why all of our justifications say because velocity, because velocity, because velocity. For example, it's also true that acceleration is positive when position is concave up. But if we said on the interval from 3 to 6 because position is concave up, we would not get credit because we are not given the position graph. Here's one other small but important detail. Always use parentheses when describing intervals of positive, negative, increasing, decreasing, concave up, concave down. In this case, we are talking about the interval where velocity is increasing. We have to use parentheses because right at the endpoints, right at 3, velocity is neither increasing nor decreasing. Right at 6, the velocity is increasing before 6 and decreasing after 6. But right at 6, it is neither increasing nor decreasing. So the endpoints are not to be included in the set. So we show that using parentheses. Number 9. When, if ever, is the bug moving upward? Justify your answer. The direction is indicated by the sign of velocity. If the bug is moving upward, velocity is positive. Velocity is positive on this portion of the graph. I'm going to write it in two different intervals because right at t equals 3, the velocity is equal to 0. So the velocity is positive from 0 to 3 and from 3 to 8. We say on the interval from 3 to 0 and 0 to 8 because velocity is positive. Special case, we should technically put a bracket on the 3 because right at 3 the velocity is positive and the closed circle indicates that this point is included in the domain. So we don't have to worry about the old, well, technically it's neither positive nor negative. No, it's positive, so it should be included. Having said that, if you wrote all of this but you accidentally put parentheses, I don't think anyone, including the AP graders, would mark this wrong if you wrote it this way. So when in doubt, use parentheses. Number 10. When, if ever, is the bug's speed increasing? Justify your answer. Speed is increasing when velocity and acceleration have the same sign. However, we do not have the graph of acceleration, so you must not mention acceleration in your justification. For example, speed would be increasing when velocity and acceleration are both positive, but since we can only mention velocity, we would say because velocity is positive and increasing. Similarly, speed would be increasing if velocity and acceleration were both negative. But since we can't mention acceleration, we would have to say because velocity is negative and decreasing. Velocity is positive and decreasing on this interval, so the speed would be decreasing. Do you hear how these velocity words sound opposite? So you know the speed is decreasing. On the other hand, velocity is positive and increasing on this interval. Do you hear how these velocity words sound similar? So you know the speed would be increasing on this interval. From 6 to 7, velocity is positive and decreasing. In other words, velocity is positive, but acceleration is negative. Therefore, speed is decreasing on this interval. On the interval from 8 to infinity, velocity is negative and decreasing. Do you hear how the velocity words sound similar? So you know the speed is increasing on this interval. Here's another way to think about it. Velocity is negative. The decreasing part means acceleration is negative. So velocity and acceleration are both negative, and that's how we know the speed is increasing. But you can't mention acceleration, so we're going to have to stick with velocity is negative and decreasing. Bottom line, the speed is increasing on these two orange intervals, from 3 to 6 and from 8 to infinity. We say on the interval from 3 to 6 because velocity is positive and increasing, and on the interval from 8 to infinity because velocity is negative and decreasing. Number 11. Sketch and label the acceleration function a of t and the position function y of t on the axes given. Let y at 0 equal -1. Let's start by graphing the position function based on the velocity function. So we're going to focus on this part of the chart. The first step is to separate the velocity function into intervals of increasing and decreasing. I put these vertical lines in to indicate where velocity changes from decreasing to increasing or increasing to decreasing. Next, let's add some more vertical lines to separate velocity into intervals of positive and negative. Velocity changes from positive to negative right here at t equals 8. Let's go back and label velocity as increasing or decreasing in each of these intervals. Next, let's label velocity as positive or negative in every interval. Finally, wherever velocity is 0, the position function will have a horizontal tangent line. So I'm going to put a little horizontal mark here and here where velocity is 0 to remind me to form a horizontal tangent line in the graph of the position function at these values. Now let's translate this information about velocity into corresponding information about the position function. For example, wherever the velocity is decreasing, the position will be concave down, and wherever the velocity is increasing, position will be concave up. In addition, wherever velocity is positive, the position will be increasing, and wherever velocity is negative, the position will be decreasing. We can now use this information about the position function to sketch the graph of y of t. But first, remember we are told that y at 0 is -1. So we're told to start here. In this first interval, y is concave down and increasing, and it needs to finish off at a horizontal tangent line. So here we go, concave down and increasing and finishing out at a horizontal tangent line. Notice we don't have to hit this mark. We just need to level out at a horizontal tangent line. In the next interval, y is concave up and increasing. No horizontal tangent line. So here we go, concave up and increasing, and that's it. In the next interval, y is concave down, increasing, and rounding out at a horizontal tangent line. So here we go, concave down, increasing, and rounding out at a horizontal tangent line. In the last interval, y is concave down and increasing. So here we go. Whoops, I made a mistake right here. Wherever velocity is negative, position should be decreasing, not increasing. So on this last interval, y should be concave down and decreasing. So something like this. Just put an arrow on it, and that's the end of y of t. Now we slide over to this part of the chart to sketch the graph of the acceleration function a of t. We need to translate this information that we recorded about the velocity function into information about the acceleration function. For example, wherever velocity is increasing, acceleration will be positive. Wherever velocity is decreasing, acceleration will be negative. So now we know whether acceleration is negative or positive in every interval. The following information is not on this chart. However, remember, acceleration is the derivative of velocity, just like velocity is the derivative of position. So wherever velocity is concave up, the acceleration will be increasing, just like wherever position is concave up, velocity is increasing. Wherever velocity is concave up, acceleration is increasing. And wherever velocity is concave down, acceleration is decreasing. So let's go back and label velocity as concave up or concave down in each of these intervals. Actually, I just realized we need another vertical line to show where velocity changes concavity. So velocity is concave up, and then somewhere in here it becomes concave down. Now I can continue labeling velocity as concave up or concave down in each one of these intervals. Now let's use this information about the concavity of velocity to label acceleration as increasing or decreasing in each of these intervals. One more piece of information. Wherever velocity has a horizontal tangent line, acceleration will be 0, and that's a graph we are about to draw. So velocity has a horizontal tangent line right here, so acceleration will be 0 right here. So we need to be sure to hit this point when we draw the acceleration curve. Velocity has another horizontal tangent line right here, so acceleration will be 0 here as well. It's time to sketch the graph of acceleration. In the first interval, acceleration is negative and increasing, and we need to hit this point. So here we go, negative and increasing and hitting this point. It's getting a little bit crowded in here, but hopefully you can distinguish between the colors I'm using. In the next interval, acceleration is positive and increasing. So it's going to be positive and increasing in this small interval right here. I'm sort of bending down because I know we have to come back and hit this point. On this next interval, we are positive and decreasing for acceleration. So positive and decreasing, and then we're hitting that point. In the next interval, acceleration is negative and decreasing. So here we go, negative and decreasing. And in the last interval, acceleration is negative and increasing. So, negative and increasing for this last little part. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.